What if empty space isn't really empty? For generations, we've imagined space as an enormous void, a vast emptiness separating stars, planets, and galaxies. But modern physics tells a very different story. According to quantum field theory, what we call empty space is actually filled with invisible quantum fields. Every fundamental particle we observe is understood as an excitation, a ripple, within one of these underlying fields. Even the vacuum itself isn't perfectly still. It constantly fluctuates, producing measurable phenomena such as virtual particles and the Casimir effect. In other words, the vacuum has structure. Now consider plasma, the fourth state of matter. Unlike solids, liquids, or gases, plasma naturally organizes itself under electromagnetic forces. It forms filaments, vortices, double layers, and remarkably complex structures. Across the universe, from lightning to the sun to distant nebulae, plasma demonstrates an extraordinary ability to self-organize. Modern science has also shown that resonance creates stability. Standing waves produce persistent patterns. Harmonic oscillations allow coherent structures to emerge from seemingly chaotic motion. These ideas are not speculation. They are well-established areas of modern physics. But what if they are all connected? What if the vacuum, electromagnetic fields, plasma, and resonance are all manifestations of something even more fundamental? This is where the theory of magnetivity introduces a new hypothesis. Rather than viewing space as simply containing fields, magnetivity proposes that reality itself may consist of a coherent magnetic plasmatic continuum, a universal substrate possessing both electromagnetic and harmonic properties. Within this framework, elementary particles are no longer viewed as tiny solid objects. Instead, they become stable resonant vortices within this universal field. Atoms become long-lived harmonic attractors. Matter itself emerges through coherent resonance. Gravity is no longer treated as a fundamental force, but as an emergent consequence of coherence, gradients within the substrate. Even space-time and geometry become expressions of harmonic equilibrium rather than independent entities. This is a profound shift in perspective. It does not replace established physics. Instead, it asks whether gravity, electromagnetism, matter, and space-time might all emerge from a deeper organizing principle. This concept shares similarities with several scientific ideas. Quantum field theory treats fields as fundamental. Plasma cosmology explores the importance of electromagnetic processes on cosmic scales. Superfluid vacuum theory imagines space-time behaving like a fluid. Physicist David Bohm proposed an underlying implicate order connecting reality beneath what we observe. John Archibald Wheeler suggested that information itself may be fundamental, and Nikola Tesla famously emphasized the importance of frequency, vibration, and resonance, although many popular quotations attributed to him are difficult to verify. Magnetivity is inspired by these ideas, but it is distinct from all of them. Most importantly, magnetivity remains a hypothesis. Science advances through evidence, not elegance. No matter how beautiful a theory appears, it must make predictions that can be tested. Could it predict subtle changes in gravitational lensing? New polarization signatures within the cosmic microwave background? Laboratory resonance effects beyond conventional electromagnetism? New plasma behaviors? Or measurable deviations in high-precision interferometer experiments? Only experiments can answer these questions. If those predictions are confirmed, the theory grows stronger. If they are not, the theory must evolve or be abandoned. That is how science works. Perhaps the greatest strength of magnetivity is not that it claims to have all the answers, but that it asks a new question. What if matter, gravity, electromagnetism, and the very structure of space-time are all expressions of one underlying principle, a universe organized through coherent resonance? Whether future research supports or challenges this idea, its ultimate success will depend on mathematics, observation, and experimental evidence. Because every great scientific revolution begins the same way, with a new way of looking at reality.